Hi guys, welcome back. All right, so we are going to talk about this another one. Let's share screen. This one here. Share. All right, today we are going to talk about the metabolism, and this one basically is an extension from our previous lecture in the large molecule. So here we will going to talk about more detail about this molecule being used in our body. How is that processed in the body? So, so in this talk, we are going to talk about the metabolism in three important molecules. We will focus on their energy storage and also energy usage. Carbohydrates, lipid, and the protein. Metabolism basically is a chemical reaction in the cell, and that includes two portions. One is the catabolism, that is a breaking down or from the large molecule, and the other one is anabolism, which is assembling. We talked about this already, and so this is not totally new to you guys. This is gonna be relatively easy because some of the material are a little bit overlapped. So you will see that this is basically the very common idea that all our organic molecules are polymers. So we have the breaking apart. It's also the hydrolysis, right? So breaking apart to form the smaller molecule and also put it together to form the large molecule when we need to store it in our body. So carbohydrate, we break it apart to form the glucose, for example. We can burn through glucose. If we don't burn, we store it. Store it as what? Store it as large molecule polymers. It's either the glycogen in the muscle cells and the liver or triglyceride. It's a polymer of fatty acid. In what? In the adipocyte. So it's all begin by our food. We can generate some of these essential, some of these nutrients, but for those we cannot, are called essential nutrients. So it's all coming from the food, so we need to get the food, either buy it or purchase it. It's same thing, purchase it, or collect it. In the old time, we collect the food. And then we eat it, we chew it, we make it from the large molecule, from a starch, from the meat, right? Proteins, lipid, and fruit, vegetables. We break it apart, start chewing it from the mouth, and chewing it. All this process is hydrolysis. We break it apart from large one to smaller one to smaller one, which in each one, we need an enzyme. So in this case, the picture showing you here is the example of the carbohydrate digestion. So here we have the saliva, have this alpha amylase to break the starch apart. Starch are the polysaccharides, so we break it apart. Polysaccharides to break it apart. Then we have disaccharides. In the small intestine, we have this pancreas, our amylase again to break it further apart. In the small intestine, then we start to absorb in these small molecules. So we need to break it apart because all these cells, they only take in the small molecules. They cannot take in the large molecules. So chewing, digesting is an important process. We also talk about the lactose intolerance because the person doesn't have the lactase, lack of the enzyme needed to break apart the lactose. So we talk about those. What's new here then? One thing new here is that we need to learn that, okay, one thing new is that in our small intestine, we actually talk about this a little bit, that whatever you eat, whatever you digest, the place where it starts to enter into our cells or our body is the small intestine. So that's a quick question, okay? So where in our body, which organ is a major organ to absorb our food? That is small intestine. So here is the small intestine, is nutrients are absorbed in the small intestine. If you remember your anatomy, you should know that small intestine has 3 segments: duodenum, jejunum, and the ileum. 3 segments. So that is the small intestine. If we ask that which cells in the small intestine absorb these nutrients include carbohydrates, monosaccharides, proteins, small peptide maybe, and amino acid, that's a monomer, lipid, very simple form of lipid. So if we ask which cells are the cells to absorb these nutrients, your answer would be enterocyte. So that's the answer. So you have 2 questions now. Which one, which organ, which 2, which cells? So enterocytes are the cells in the small intestine. It's right here. This one is on the wall. I think we have something like, so here is here is one of these enterocyte in the small intestine, and that is the cell to absorb this. You can see that this is on top of it. That is one enterocyte. On one, it has microvilli, and that is, increase the surface, increases the space, so we can capture this monomer and absorb it into our body. On the brush membrane, it contains several digestive enzymes. If it's not totally broken apart at this moment, it can be further broken apart. So that's digestive enzyme to break apart. So for example, that here, this one here, enterocyte, one here, one here, one here, one here. On the membrane, we have the enzyme to break further apart of these disaccharides to become monosaccharides, and then it can be absorbed. This is the slides we used earlier. So, but we only talk about the carbohydrate at that time. Here we know carbohydrates is absorbed in the small intestine via enterocytes into the body. This is amino acids, so this is protein. Break it apart, large protein to break it apart to become oligopeptide, small peptide it means, plus amino acid. So here we have 3 amino acids, here 1 amino acid. So it can enter into the cell and be absorbed into this enterocyte. So enterocyte is a cell to do the absorption. Carbohydrates here, proteins here, and the lipid here. So lipid is permeable through the membrane, so they can freely enter into the cell. When they enter into the cell, which cell? Enterocyte. That's right, enterocyte. So enterocyte absorb all this, and lipid enter into the enterocyte, will then pass into the body, and they first form the chylomicron. That is this little like particles. And then it will enter into the lymphatic vessel. So other here, carbohydrates, monosaccharides enter into the blood vessel. So they enter into this capillary and transport in the blood. Proteins also enter into the blood. Doesn't say here, but it enter into the blood. So protein, amino acids, carbohydrates are all transport in the blood. Lipid is different. Lipid, when it enter into our body, they first enter into the lymphatic vessel. So this is in our small intestine. In our small intestine, we have very rich vascular system. And this lymphatic vessel in the small intestine has a special term, special name is called lacteal, right here, lacteal. So it's right here, lacteal. So this is a lymphatic vessel. And then lymphatic vessel will, in the end, will flow back to the vein, and then flow into the vein will go into the systemic circulation. And over there, it will form this lipoprotein. So from the HDL to LDL, triglyceride will be absorbed into the cells. So that's the absorption. And one common theme of all these three important nutrient molecules is that they all reabsorbed in the small intestine and in the enterocyte. The cell's name is enterocyte. The organ is small intestine. Two other questions is that proteins and carbohydrates, they are absorbed directly into the blood. Lipid, they first enter into the lymphatic vessel. This lymphatic vessel is called lacteal. And the lipid into the lacteal is called chylomicrons. All right, so that is absorption. Now, when we have this, we are not going to burn it right away, right? Because we need to, when you get the money, will you spend them right away? No, right? You got paycheck, you got paid, then you put it in your pocket, right? That's the first thing you do. You won't just spend it out immediately. So you put it into your pocket. So we need to store our food. When we eat it, we don't use it right away. We need to store it. So the way we store it is to store in these three forms. If it's carbohydrates, it can be stored as glycogen. Excessive glucose can be stored as triglycerides in the adipocytes. Lipids are stored as the triglyceride in the adipocytes, in the liver and adipocytes, but the major one is the adipocyte. Proteins, amino acid can be used to form proteins. We learned that protein is not the main source to be burned. They are the one to provide body function. So proteins are very carefully decorated, folded to specific structure to become an enzyme, to form this insulin, hormone, etc. So proteins, we don't really burn them unless we are truly have no other choice, like very starving. So protein in all cells require protein. Your muscle require protein. So there are some people ask, like maybe you don't have that question, but some people ask, if I work out very hard, would I in the end start to burn the protein in my muscle? No, you have so many things to burn. If you work out, if you exercise, you first burn glycogen, and then you burn your triglyceride. And only until maybe you run the marathon and for many days, then you start to or starving, you know, there's time that people have no food. Famine, I forgot the term. So no food then that people will have no choice, but the body will have to start to burn the protein. All right, so this is glycogen, polysaccharides, 1 carbohydrate, 2 carbohydrates, glucose, monosaccharides connect together to form this glycogen. Glycogens are the form of carbohydrates stored in our muscle and the liver. Triglycerides is a form we store fuel in our adipocytes and the liver. So triglycerides are the most common energy storage molecule and the second most commonly used fuel in the cells. So they are in general most abundant because we don't use them right away. We use glucose first. And if we burn out the immediate glucose, we start to convert glucose from the glycogen because that's easier. And in the end, if we use all the glycogen, then we start to use triglyceride. So these triglycerides are stored in the adipocytes. Fatty acids are stored as a triglyceride. Glucose can also be stored as the triglyceride in the liver and the fat cells in the adipocytes. So this is where we store our triglyceride. It's in the adipose tissue. Adipose tissue contains all these adipocytes. So that's your so-called fat, right? And this is one of our fat cells, adipocytes. So you can see that this is very amazing cell. I feel we have been labeled this a bad name for a long time. I really don't think it's something that we should, you know, label it that bad. To me, this cells is amazing. I mean, you can see that the whole cells basically do nothing but store our fuel, our food as a triglyceride. And for a very long time, like if you buy the food and you put it in your refrigerator, or it will be spoiled. And our body has a storage for it. And we don't need to put it in the refrigerator. It's in the cell. And you know, it's such a big capacity. It's only for the triglyceride. So when you eat, you have first store the fuel as the glycogen in the muscle. And if you have more of this glucose, then you store it as the triglyceride in the adipocyte. So it's very much like if you get the money, right? You got a paycheck. You first put it in your pocket. That's your glycogen, right? And then if you need it, you use it right away. So we burn glycogen first, glucose first, then glycogen. We use it right away. But if you do have a lot of money, which is a good thing, right? Who doesn't like money? Then you do what? You put it in your bank, right? You have a bank account, and then you put your money in the bank. That is your triglyceride. That is your excessive money. So nobody will complain that they have too much money. And that's where we store our fuel. So same thing that if we use our money, we use it from our pocket. And then if we use all the money in the pocket, then we go to the bank to to get some more money. And so the adipocytes are the bank account that if you use all your glycogen, then you come to the adipocytes to use this stored fuel. So a little bit fat is not a bad thing, you know. It's cholesterol in a way that is not good, but triglyceride, you know, it's okay. I mean, it's there a little bit fat, you know. It's a good thing. I mean, body needs some place to store this excessive food. But cholesterol is bad because they are not a good source for energy, and they will stay in the lipoprotein, form this low density lipoprotein, and they are not stored in all these cells. They circulate around in the blood, and they will induce inflammation and induce several diseases. So cholesterol is comparably, you know, a little bit is okay, but too much really is not a good thing. All right, so that's fat. Then we have this stored, right? We don't use it, then we need to use it. Then how our cells use it. The way we use it is to use it several ways, but if we are focusing on the fuel, then these are all used in the mitochondria. Mitochondria is a place to generate, its expertise is to produce the ATP from this fuel. So we will have triglyceride to form the fatty acid, glycogen to form the glucose, you know, basically that. Hydrolysis to break apart, and protein to form the amino acid. And then they will enter into the mitochondria to produce ATP. We kind of know part of this already. We talk about the organelles. We learned that mitochondria produce ATP through the oxidative phosphorylation. That oxidative phosphorylation is produced in the electron transport chain. The location, inner membrane, that's right, is in the inner membrane of the mitochondria. And that's the place where we produce ATP. This electron transport chain has the electron transport, and that electron will be received by something which is oxygen. So that's where we need oxygen, and that will be reduced to water. Oxygen, some electron, and proton, it will form water. That's why we need to breathe in oxygen. And the electron transport chain require the accumulation of proton gradient, the hydrogen, who donate the hydrogen, NADH and FADH2. Where do we get the NADH and the FADH2 from? They are from the citric acid cycle. And when they produce the NADH and FADH2, they also produce CO2. That's why we need to breathe it out, CO2. So we basically talk about that. We only need to explain how to connect this citric acid cycle with the three different monomers. So let's start by glucose. Okay, glucose is burned is used in mitochondria. Okay, but the link is that we need to link glucose with this citric acid cycle. It is right here. So glucose first need to go through the glycolysis. Then it will form pyruvate. Pyruvate is one that mitochondria can use. Pyruvate enter into the mitochondria. then mitochondria will convert pyruvate to acetyl-CoA. The entering proteins in the acetyl-CoA is this one here. This is citric acid cycle. The entering molecule into the citric acid cycle, the entering molecule into the TCA cycle is acetyl-CoA. It's right here. So this is the citric acid cycle. This is a cycle of this one here, and that comes from the entering molecule is this one here. The citric acid cycle. So to produce NADH, FADH2, to go through this cycle, the entering molecule is the acetyl-CoA. So this is one. Everything else, glucose, need to become pyruvate. And then pyruvate will form the acetyl-CoA. Okay, so that is this one here. So once you become the acetyl-CoA, you enter into this citric acid cycle, then you get on the train and go through this process. Enter this machine and to start to produce NADH and FADH2 electron transport chain produce ATP. So the only thing you need to know is that that's the acetyl-CoA is the entering molecule, and that acetyl-CoA coming from the pyruvate coming from the glucose. And this process though, glucose to pyruvate, this process is called glycolysis. It's not just hydrolysis. It's glucose has 6 carbon to be split to become 3 carbon each, and that is pyruvate. So it's glycolysis to break apart glucose. So let's go back to this one here. Glucose through the glycolysis to form pyruvate. Pyruvate then enter into the mitochondria to produce the acetyl-CoA. Acetyl-CoA then enter into this citric acid cycle. So this glucose catabolism goes through 2 stages. The first stage is called glycolysis. This glycolysis is the one that doesn't require oxygen. So this process is also called anaerobic reaction. And that produce 2 ATP. It's not like totally useless. It produces 2 ATP, but not a lot. If we provide them oxygen, then this pyruvate enter into the mitochondria to convert to the acetyl-CoA to be processed through the citric acid cycle, through the electron transport chain, then this will produce 34 ATP. So that's a lot more. So this is a process with oxygen. This is process without oxygen. So let's go back to this slide. This slide summarizes it. Glucose catabolism goes through 2 processes: anaerobic metabolism or anaerobic reaction. This is the one, it doesn't even need mitochondria. It's in the cytosol. It doesn't even need mitochondria. And it doesn't need O2 either. It produces a little bit ATP, and its end product is lactate. So this end product is the lactate. So that's the anaerobic metabolism. This process is also called, the main process is glycolysis. And if we provide them oxygen, then glucose will form the pyruvate. It will then enter into the mitochondria, and over there it form the acetyl CoA, and then it enter into the citric acid cycle or Krebs citric acid cycle. So that's two process over there. So this picture showing you that glucose goes through this glycolysis to form pyruvate, and without oxygen, it will be basically just like it here. But if there's oxygen, pyruvate enter into the mitochondria, convert to the acetyl CoA citric acid cycle, produce more ATP. Without oxygen, pyruvate will be fermented to form the lactate, and this process doesn't require oxygen, but still we use glucose to produce very small amount of ATP. It's not like nothing, but it's much less efficient compared to the oxidative phosphorylation. So the end products of the glycolysis is the pyruvate. It's right here, pyruvate here. Glycolysis is pyruvate, but anaerobic exercise, the end product is the lactate. Glycolysis is pyruvate. Then pyruvate enter into the mitochondria to form acetyl CoA. Then acetyl CoA enter into the citric acid cycle to produce NADH and FADH2, which will donate its hydrogen and for the electron transport chain to produce ATP. So we mentioned about this one. Acetylcholine is the molecule that needed in order to go through this machine to produce the NADH and the FADH2. Where is this citric acid cycle is conducted? The matrix space in the mitochondria. So we already talked about that. The NADH and the FADH2 donate its hydrogen to put into the intermembrane space, and that hydrogen gradient push through this channel and to convert the ADP to ATP. Push through this channel to produce ATP. And that electron can be reduced by oxygen. Oxygen here to form the water. So oxidative phosphorylation, oxygen is needed, and the NADH and the FADH2 donate its hydrogen, and in the same time, the electron is transported along this chain, and to be reduced by oxygen. In the same time, hydrogen or proton is accumulated, and that gradient will push it to produce ATP. So the entire process, glucose catabolism, is like this one here. Glucose through this glycolysis, and don't need to worry about this figure here. So that basically is this one here. All right. So glucose goes through this process, glycolysis, to form pyruvate. In the same time, it produces 2 ATP. If there's no oxygen, then pyruvate will form the lactate. That's it. If there's pyruvate, then sorry, if there's oxygen, then pyruvate enter into the mitochondria, and then it was converted to the acetyl-CoA, enter the citric acid cycle to produce NADH and FADH2. Electron transport chain will use those to produce ATP. So here, this part is anaerobic. This portion is aerobic. No oxygen, with oxygen. So the border line is here. No oxygen. This part is oxygen. No oxygen. So just it make it more clear right here. So anaerobic metabolism without oxygen, glucose, glycolysis to form the pyruvate. So quiz question could be that what's the end product of the glycolysis? Pyruvate, that's right. Multiple choice, just choose this one. And the pyruvate need to enter into the mitochondria to be converted to the acetyl-CoA. So the entering molecule to the citric acid cycle is the acetyl-CoA, right here. So, or right here, pyruvate need to become the acetyl-CoA. Then it can enter into the TCA cycle. All right, so without oxygen, it's only produce 2 ATP, then that's it. With the oxygen, it will form the aerobic metabolism. This one produce a lot more ATP. Now, with this lactate, this is commonly seen when we do exercise because it's not like we don't have oxygen. It's just oxygen is used very quickly. Earlier, we talked about the blood. We know hemoglobin carry oxygen into the local tissue. And the local tissue see oxygen as money. So all the cells see the oxygen will grab it and use it. When we exercise, the supply doesn't meet the demand. So sometimes muscle burn glucose without oxygen. Not all the cells have enough oxygen to be used. So the oxygen distribution will not be even. And some cells will have to run without oxygen. Some cells will run with oxygen, but some cells will run without oxygen. So some muscles, after very intense exercise, some muscle will produce fair amount of lactate. And that will lead us to introduce another important mechanism. It's called Cori cycle. So this Cori cycle is how our body uses those lactate. So basically, muscle with the intense exercise produce lactate. This lactate will go to the blood, go to liver. Liver can convert this lactate back to glucose. Then transport that glucose back to the cell. Cell will use it. So this circle is called Cori circle. Cori circle, which organ will convert lactate to glucose? Liver. So basically, that's the question that you will see. So that's the glucose. That one's easy. So we basically go make it simple, like glucose form pyruvate. This process is glycolysis. Pyruvate enter into the mitochondria to form the acetyl-CoA. It's right here. Pyruvate enter into the mitochondria to form the acetyl-CoA. This is a machine. This is called a wheel, right? And then it produces NADH and FADH2. And that will be used to produce ATP. All right, so that's glucose. And then next up is the lipid. How do we burn lipid? Very easy. If you know glucose, lipid is just like a piece of cake. So what lipid does is that we have this fatty acid. Fatty acid right here. So it goes through basic, very much the same process like glucose, with only one shortcut. The fatty acids directly, because fatty acid, let me delete this one because I don't like that. Fatty acid, sorry, so let's not worry about this one here. It's fatty acid to the acetyl it's right here. Fatty acid enter because this is lipid soluble. Enter into the mitochondria. It directly convert to the acetyl in the mitochondria. And then it goes through this citric acid cycle to produce ATP. So that's very much the same. It's just, it skip some process, skip this glycolysis process. It's fatty acid can directly convert it to the acetyl and then become acetyl and then go into the citric acid cycle to produce NADH and FADH2. This process has a name though. Fatty acids to the acetyl. This process is called beta oxidation. So fatty acids are broken down to generate acetyl because fatty acids, if you may remember, it has a very long carbon chain. So it's a C a lot carbon chain. So basically that each time it will, and the acetyl is not that long. Acetyl maybe it's only this many molecule. So each time it cut it, and to move this C down here, COO actually, down here, down the next one. So each time it cut it, and this cut is cut at the beta carbon. So here we have alpha carbon, beta carbon. So it cut in beta carbon. And that small molecule will be used to convert to the acetyl and be used. So one fatty acid can be cut many, many times. So single molecule can produce a lot of ATP. And the number of ATP produced from a single molecule depends on the length of the fatty acid. If it's very long, it can be 12, it can be 16, it can be 18. So depending on the length, the amount of ATP to be produced can be different. But either way, they produce a lot of energy. So that's a process that fatty acids convert fatty acid to acetyl through the beta oxidation. So this is a term you will see in your quiz. Where is it? Beta oxidation is in the matrix of mitochondria. So this one is processed in the mitochondria. And what's the process to convert fatty acids to the acetyl-CoA? Beta oxidation. So this one just gives you a visual idea about this beta oxidation. So acetyl-CoA is short. We need to cut it. This cutting is the beta oxidation. And because fatty acids has long, here we can see long chain, so it can be cut many, many times. So one fatty acid can produce a lot of acetyl-CoA. Each acetyl-CoA can produce a lot of ATP, so each fatty acid can produce a lot of ATP. So it's very efficient. This triglyceride, these fatty acids are very efficient. So this one summarizes both. Fatty acids and the glucose basically go through the same pathway when they are burned in mitochondria. They all use the same machine. It's just in the beginning, they may appear differently, glucose, fatty acid. But when they enter it, they all become acetyl-CoA. Acetyl-CoA is the entering molecule into the citric acid cycle. So let's look at the glucose. Glucose first need to convert to pyruvate. This process is called the glycolysis. Pyruvate enter into here. This dashed line is the mitochondria. Pyruvate become convert to the acetyl-CoA, then it enter this machine, produce NADH, FADH2, and NADH and FADH2 will be used in the electron transport chain through this oxidative phosphorylation to produce ATP. So that's glucose. Fatty acids outside of the cell, they enter into the cell because this is lipid, and then they enter into the mitochondria. Again, it's lipid. Inside of mitochondria, fatty acids is converted to the acetyl-CoA through the beta oxidation. And then the remaining is the same. Acetyl-CoA enter into the citric acid cycle, produce NADH, FADH2, and then those are used in the electron transport chain to produce ATP. So these two basically coming from two different ends, but in the end, they all become acetyl-CoA. So the term you need to memorize is this one here. Sorry, where's my pen? For the glucose, the term you need to memorize is the pyruvate, right? Because this is the end product of the glycolysis. The term you need to memorize here is beta oxidation, because only then fatty acids become the acetyl-CoA. Acetyl-CoA is their common end product in a way. So it's a common, like they all converted to acetyl-CoA. Then acetyl-CoA will go through the same process, go through that process, the citric acid cycle, and to produce, to be used in our mitochondria. All right, so glucose, fat. In fact, we need to talk about one thing, which is ketone body. Right here, ketone body. When fatty acid is used to produce acetyl-CoA, the side products is to produce ketone body. Ketone bodies. There are three ketone bodies. Acetoacetate, acetone, beta hydroxybutyrate. So there are three ketone bodies. These ketone bodies will be used, but if we produce them too much and too fast, they will make our blood become acidic. And that is it's a disease, that is a condition that we may see in patients who does not use glucose as their major energy source. Because if we use glucose, we don't have these side products. We use glucose as our main source, fatty acids or triglyceride as a secondary support. But for some patients or some disease that they cannot effectively use glucose, they will have to fully depend on the fatty acids. And in that situation, they will have the accumulation of ketone body, and they may lead to into the blood, increase the blood acidic level. And this disease, this condition is commonly seen in patients with diabetes. Yeah, with diabetes. That's because that the diabetes patient, even though it's not like they don't eat glucose, they eat glucose, even they have hyperglycemia, high glucose level in the blood, but those blood remain in the plasma. Sorry, those glucose remain in the blood. They cannot enter into the cell because there's no key to open door for them. What's the key? Insulin. The cells build this insulin resistance. They are not sensitive to insulin, so they are not open door for the glucose. So cells is starving. They need glucose, but they don't open door for the glucose. And at that time, that cells need to burn something. They will transport. Fatty acids doesn't need door, doesn't need someone to open door because those are lipid. So fatty acids coming in and cells just use whatever they have, right? No glucose, fatty acids abundant, then and that's why that in some, I know this is not like universally true, but in some like a diabetic patient, you may see them very skinny. I know that in hospital, a lot of diabetic patients, they are not that skinny, but one of my friends who has a very chronic diabetes, he is very skinny, he's in a very good shape. So because that these patients, they burn triglyceride, they burn the lipid. And in that time, they will produce a lot of ketone body, and that will make the blood become very acidic. And this is condition called diabetic ketoacidosis. Here. And this is not good because acidic level in the blood become very acid, and that actually can cause a lot of damage to our body. So we have the carbohydrates, lipid, now protein. One thing about the protein is that protein can be burned, but it's the last resort. We don't usually do that. Okay. Protein, when we break down protein, we have different amino acids. In our body, we have about 20-some type of amino acids. So each one could be different. We cannot kind of summarize it like this one here, fatty acids. All fatty acids is very much the same, even though it could be double bond, could be said fat, unsaid fat, could be long, could be short. But in the end, it's very much the same. We just cut it. Like this one here, we basically just cut it, package it, and convert it to the acetyl-CoA. It's very much the same. Glucose, same thing. Because no matter how big your glycogen it is, like this one here, as we store it, no matter how big your glycogen is, we basically just cut one piece at a time, right? So it's in the end, it's only glucose. So it goes through this process, glucose. No matter how big or how small your glycogen is, we cut it, they get this glucose, enter it, and do this process. So for the glucose and the fatty acids, it's very kind of like common process, universal common process. Amino acid is different. Amino acid, we have so many different kinds. And good thing is that we don't burn them like we burn fat and carbohydrates. So burning them is really the last resort, last step. If we do burn them though, there are two ways to burn them. We can burn them like glucose, or we can burn them like fatty acids. So amino acids can be classified into two types. One type is called glucogenic amino acids. The other one is called ketogenic amino acids. So glucogenic, they are a group a group of amino acids belong to this type, they will be converted into glucose, then they'll be burned. Ketogenic amino acids will then be degraded to the acyl-CoA-like fatty acids. And in the same time, they also have style product to produce ketone body. And that's how it's burned. But protein and amino acids catabolism, breaking apart, is highly regulated because they are essential like bricks in our body. So we don't usually burn them. All right. Okay, so that's it. Next one, we will talk about the electrophysiology. And with this one, let me know if you have any question.